Matter, energy, and space-time itself were compressed into an infinitely small and highly energetic state. This singularity represented a moment where the laws of physics as we know them, particularly general relativity, around 3000 Kelvin, allowing electrons to combine with protons and other atomic nuclei to form in the CMB that defies standard cosmological predictions. Additionally, scientists are still searching for direct evidence of gravitational waves from the inflationary epoch and working to better understand the nature of dark matter and dark energy. The CMB continues to be a vital tool for cosmologists, offering a window into the universe's earliest moments and providing invaluable data that shapes our understanding of the cosmos. The formation of the universe's first elements, a process known as nucleosynthesis, occurred within the first few minutes after the Big Bang. This period, called Big Bang nucleosynthesis, BBN, was crucial for shaping the elemental composition of the early universe. During this time, the universe had cooled from an incredibly hot and dense state to a temperature of about 1 billion Kelvin, 10 to the power of 9 Kelvin, allowing protons and neutrons to combine and form atomic nuclei. The process was governed by the strong nuclear force and the delicate balance between the rates of nuclear reactions and the rapidly decreasing temperature and density of the universe. In the first fraction of a second after the Big Bang, the universe consisted primarily of quarks and gluons, which soon combined to form protons and neutrons. Initially, there were nearly equal numbers of protons and neutrons, but as the universe cooled, free neutrons became unstable and began to decay into protons, electrons, and neutrinos. The neutron-to-proton ratio stabilized at around 1 neutron for every 7 protons by the time nucleosynthesis began. Approximately 3 minutes after the Big Bang, the first and most abundant element formed during nucleosynthesis was hydrogen, specifically its isotope protium, 1H, which consists of a single proton. Some protons and neutrons combine to form deuterium, 2H, a heavy isotope of hydrogen. As the temperature remained high enough for nuclear fusion, deuterium nuclei fused to create helium-4, which contains 2 protons and 2 neutrons. Helium-4 became the second most abundant element in the early universe, accounting for about 25% of the universe's elemental mass, while hydrogen constituted roughly 75%. In addition to hydrogen and helium, trace amounts of lithium and beryllium were also produced during Big Bang nucleosynthesis. However, the formation of heavier elements was limited due to the absence of stable nuclei with atomic mass numbers of 5 or 8, which created bottlenecks in his theoretical calculations based on the conditions of the early universe. This agreement provides strong evidence for the Big Bang theory and helps constrain key cosmological parameters, such as the density of ordinary matter and the expansion rate of the universe. Despite its success, there are some challenges in understanding nucleosynthesis fully. One notable issue is the so-called lithium problem, where the observed abundance of lithium in ancient stars is lower than predicted by Big Bang nucleosynthesis models. This discrepancy remains an open question in cosmology and nuclear physics, prompting ongoing research into potential solutions, such as new nuclear reaction rates or exotic particle interactions. In summary, the first few minutes of the universe were a critical epoch during which the lightest elements were formed. This process set the stage for the chemical evolution of the cosmos and the eventual formation of stars, galaxies, and planets. Understanding nucleosynthesis not only sheds light on the early universe, but also provides a foundation for tracing the origins of the elements that make up everything around us today. The Dark Ages of the universe refer to a period that began approximately 380,000 years after the Big Bang and lasted for about 400 million years until the formation of the first stars. This era is called the Dark Ages because no sources of visible light existed, and the universe was filled with neutral hydrogen gas, which absorbed any emitted radiation. Understanding this phase is crucial for tracing the trend when the universe had cooled enough to roughly 3000 Kelvin for protons and electrons to combine and form neutral hydrogen atoms. This event marked the decoupling of matter and radiation, allowing photons to travel freely through space. These photons make up the cosmic microwave background, which provides a snapshot of the universe at the time of recombination. However, after the release of the CMB, the universe was devoid of luminous sources, leading to a long period of darkness. During the Dark Ages, the universe continued to expand and cool. The temperature of the cosmic gas gradually decreased, eventually dropping to just a few degrees above absolute zero. Without stars or galaxies to emit light, the universe was mostly invisible to telescopes that rely on optical wavelengths. However, other forms of radiation, such as weak radio waves, would later provide clues about this hidden epoch. Although visually dark, the Dark Ages were not entirely uneventful. Gravity began to amplify small density fluctuations present in the universe after the Big Bang. These fluctuations were remnants of quantum variations, stretched to cosmic scales during the period of inflation. Over millions of years, regions of slightly higher density attracted more matter, gradually forming the seeds of future galaxies and clusters. These gravitational processes laid the groundwork for the cosmic structure we see today. Another important event during the Dark Ages was the gradual formation of molecular hydrogen, which played a crucial role in cooling the gas clouds that would later collapse to form stars. Molecular hydrogen acted as a cooling agent, allowing dense regions of gas to reach low enough temperatures for gravitational collapse, ultimately leading to the birth of the first stars. The end of the Dark Ages came with the cosmic dawn, marked by the ignition of the first stars approximately 400 million years after the Big Bang. These massive, short-lived stars emitted intense ultraviolet radiation, which began the process of reionization. This process reionized the neutral hydrogen gas in the universe, making it transparent to ultraviolet light and signaling the emergence of a luminous universe. The reionization period lasted for several hundred million years, during which galaxies and quasars continued to form and contribute to the transformation of the universe. The study of the Dark Ages remains challenging due to the lack of direct observational data. However, advancements in radio astronomy, particularly efforts to detect the 21-centimeter hydrogen line, offer hope for uncovering more information about this mysterious period. Understanding the Dark Ages is essential for piecing together the full history of the universe, from its hot, dense beginnings to the complex and dynamic cosmos we observe today. Detecting dark matter is one of the most ambitious and complex endeavors in modern science. Although it does not emit, absorb, or reflect electromagnetic radiation, its gravitational effects on galaxies and cosmic structures are undeniable. Experiments seek to observe dark matter particles interacting with atomic nuclei in highly controlled laboratory environments. The most promising candidates for near-light speeds would age more slowly than people remaining on Earth, a concept that has profound implications for space travel and was famous. Partner will immediately be determined, even if separated by vast distances. This phenomenon, which breathtaking images and groundbreaking data that have captivated scientists and the public alike. From dropping